So tonight we have a very special lecture, which I think you're really going to enjoy. For those of you who don't know Carnegie so well, Carnegie observatories, where the astronomers work, and those of us who put on this series, are, of course, here based in Pasadena. But we're one of only 6 departments as part of the Carnegie Institution for Science. And we've had some previous speakers from one of the departments called DTM, which has a few other astronomers. But tonight we have our very first speaker from the Department of Geophysical Laboratory, which is a really interesting department based in Washington, D.C. And they do all sorts of high temperature, high pressure experiments. Tonight's speaker, Anat Shahar, will tell you all about that. I'm very excited. I saw her talk about a year ago in D.C. when I was there, and when I saw her talk, I said, we have to get her for our lecture series. And so she was the first person we reached out to this year when we put the series together. And she's going to tell you all about her very exciting work, which, has very good implications for astronomy, as you'll see. This is not Anat's first time here in Southern California. She actually spent a good amount of time here. She got her PhD from UCLA, so this is a return home for her in some ways. And in 2008, so she's the youngest staff member at our department called GL back east. So help me welcome phones. Please put your phones on silent if you haven't done that already. Excellent. So please help me welcome our speaker tonight, Anat Shahar. To the stage.
Thank you. Thank you so much. It is a real honor to be here tonight speaking to all of you and in such a lovely, lovely venue. So what I'd like to tell you about tonight is a little bit about planet formation. And this is really an exciting time to be studying or even thinking about planet formation because recent discoveries by... Oh, you're supposed to turn it off. Thank you. On YouTube, you can watch it with Star Wars, but not here. So this is an animation showing the exoplanets, the multiple planet systems that Kepler has found over the past 6 or 7 years. So the colors show you the closest planet to the star is red, and then yellow, and then green and blue. So you can see the ones that have more colors have more planets. And you can see that there are different sizes of planets. And the most important part that I want you to get from this animation is how many planets there are. So 20 years ago, we thought we were really special. We had these 8 or 9 planets in our solar system. And today, every star that you look at in the sky has at least one planet, we think, orbiting it, or maybe many, many more. And so planet formation, we started thinking about it in terms of our own solar system, but really, there's so much more to be learned. And so with Kepler, we now have a really good sense of how many exoplanets there are, at least that we found so far, and how diverse the different planetary systems are. And so a lot of what we know about planet formation, we know through astronomical observations. So these have been termed the pillars of creation. This is a Hubble Space Telescope photograph of the Eagle Nebula. And what it shows you is the birth region of stars. Okay, so we take the astronomical observations, and then for those of us like myself who are not astronomers, we try to bring them to the lab and try to understand what they're actually showing us. And so if we think about planet formation and we look at an artist's rendition of what that might look like, what we start with is a cloud of gas and dust. And that cloud of gas and dust is diffuse and it's spherical and it's slowly rotating. And as it rotates, it starts to collapse. And when it starts to collapse, most of the material goes to the center, and that's the protostar. And the rest of the material starts to flatten out into a disk surrounding that protostar. And gas and dust is just rotating around, and a lot of the gas is going inwards towards the star. So the star at the end actually makes up, at least in our solar system, more than 99% of the mass of the solar system. So all this material is going around, and most of it is going to go into the star. And so, as I said, a lot of what we know from astronomy. So this is a photograph taken by ALMA, the telescope. And what you see, or what we think we see, is exactly what I was just showing you. These concentric rings showing where planets are starting to form and where the protostar is starting to form in the middle. And so over time, all the dust that hasn't gone into the star, a lot of the gas gets expelled by this massive star in the middle, and all of the dust starts to coalesce, and it bumps into each other, and the dust grains get bigger and bigger and bigger as they bump into each other. And over time, you start getting less and less stuff surrounding the star, and it ends up in a stable configuration of planets. Now, how the dust coalesces and then turns into planets is actually very difficult to understand. We've been able to understand how the dust can get to about a meter size, and then there's a problem of how does it get from a meter to a kilometer size. But for the point of this talk, it's important just to note that this process here, where you have a lot of bigger objects, actually was very, very chaotic. Okay, it wasn't a very simple situation where planets are starting to circle around and get bigger and bigger without bumping into each other. Turns out they bumped into each other a lot. And the most famous for our purpose of a giant impact like this, where two planets bumped into each other, is how we formed our moon. So we think our moon formed from when a Mars-sized body impacted the Earth. And what I'm about to show you is a simulation done by one of our postdocs back east in DC. So what you see here is the proto-Earth being hit by a Mars-sized body, and the colors show you the extent of shock heating, okay, so how hot it was really getting. And what you see is that this body came and it merged into the Earth for the most part, and all this other stuff that's on the outside is what ended up forming our moon, okay? This is the leading hypothesis for how our moon formed. And so it was very chaotic. It's thought that Earth and Venus actually had a lot of these giant impacts throughout history. So I explained to you how the solar system formed, right? But what I really study is how the planets form themselves. And so we started with dust, and then we got bigger and bigger and bigger. And when a planet gets bigger, it starts to melt on the inside. And it starts to melt for several reasons. One is it formed so early in solar system history that it caught some of the radiogenic isotopes that decay. And that decay heats up the internal portion of the planet. Also, those impacts, like the one I just showed you, heat up a planet. The kinetic energy turns into heat, and it starts to melt the planet. And so what happens is a process called differentiation. And all that means is that the planet separates into layers. Okay, so we have, in this case, you see a core in the middle, a mantle, and a crust. It's not that simple. There are lots of other ways that planets can differentiate. Sometimes they fully differentiate, sometimes they only melt a little bit, sometimes they don't melt at all. It's pretty complicated, but for the purpose of this talk, what I'm really going to focus on is when you have a core with a mantle. So when you got so hot that the whole planet was molten, and the iron got so, it was all melted, and the iron is so dense that it sinks to the center of the planet. How do we know that we have iron sink to the center of a planet, right? So everything I just told you sounds great, but how do we actually know this? Well, one way is that nature is very kind to us, and sometimes we get samples from space that just land on the surface of the planet, okay? So in 2013, this is an example of the meteorite that fell in Russia, caused a lot of mayhem. But for a scientist who studies meteorites, this is incredibly exciting because you see the meteorite fall, right? When you see it fall, it's fresh. You can pick it up and you can study it, and you know that it just came to Earth. It hasn't been contaminated by people or by animals, right? So this was very exciting. And we have places like this, Meteor Crater in Arizona, right, where we see a huge crater in the Earth that was formed by a meteorite that fell to Earth. So the way that we know that the planets are differentiated, that they have these layers, is by looking at these meteorites. So some meteorites look like this. They just look like rocks. And there are many that we will never find because they just look like rocks on the surface of the planet, and we'll never think that they're meteorites. And what's amazing about these meteorites is that they never melted. So they formed at the same time as our solar system, as our planets, but they never melted. So they have the same composition, same starting composition as the starting composition of our solar system. And if you remember back to a few minutes ago, I mentioned that the sun in our solar system makes up 99% of the mass. So if it makes up 99% of the mass of our solar system, it must have the bulk composition of our solar system. So if you look at a plot of the composition of the sun versus the composition of these unmelted meteorites, this is a one-to-one line. You see that for the most part, they agree really, really well. So we have these meteorites that have the composition, the starting blocks, if you will, of our solar system. There are some elements that don't agree. Lithium isn't stable in stars, and nitrogen, carbon, and oxygen are very volatile, and so they don't hang around meteorites very much. But for the most part, that's really good correlation. So we have these chondrites, these unmelted meteorites, that tell us what the starting materials were for our planets. And then we have achondrites, which form from the crust of a planet or of an asteroid. And we have meteorites that are made out of pure iron nickel, okay? Mostly iron, a little bit of nickel. And these meteorites are the reason we know that there's iron and nickel in the core of planets, because huge chunks of iron fall to the Earth. So that crater in Arizona, the meteor crater, was made by a huge chunk of iron metal falling from the sky. So when we think about the interior of our Earth, right, we know we have iron. There's been a lot of many books, many movies made about the core of the Earth. So what exactly is the core of the Earth? Well, the most interesting thing about the core is that we can never sample it. Okay, so it's this amazing place in the Earth that we know is there because we have these meteorites, and I'll explain to you other reasons why we know later, but we can never get a sample of it. So as a scientist, this is both exciting and very frustrating because I can never actually see it myself. And so the largest, the deepest mine on Earth is in South Africa. It's a gold mine. It's about 4 kilometers deep. The Kola super deep borehole was something that the Soviet Union drilled in the 1970s and 80s, and it got to be 12 kilometers deep. We have these amazing, again, nature is very kind to us, we have these amazing inclusions that get brought up within diamonds that tell us about the mineralogy of what's going on in the mantle of the Earth that we can never sample. And that's great for up to several hundred kilometers depth. But the core of the Earth is down here, and this is several hundred kilometers depth, right? So there's no way we're ever going to be able to get down there. So how do we know that it's there in the first place? We have earthquakes. So earthquakes are this amazing thing that can cause terrible tragedy, but they can also give us a lot of scientific information. And so when an earthquake goes off, it sends waves into the interior of the Earth that then bounce off of layers just the way an ultrasound works, right? It bounces off of layers, and when it bounces back up, you start to see a pretty picture of what's going on in the interior of the planet. This one happens to be about 8 years old now. This one is like 4.5 billion years old, right? So the discovery of the Earth's core in 1906, Richard Dixon Oldham discovered that we had a core in the Earth by looking at seismology, by looking at the waves that were bouncing off the core. And 30 years later, Ingo Lehmann, who was a Swedish geophysicist and seismologist, discovered that we had two cores. We have an outer core and an inner core. There have been many pictures of what the interior of the planet looks like over the years. And from 1990-ish and on, we've found that the planet is very complicated. There's a lot going on in the mantle, but we're very sure that we have a solid inner core and a liquid outer core. And we know it's liquid because there are certain waves that are released by earthquakes that don't go through liquid. And so they just stop. They cause a shear, and because they can't go through liquid and they just stop, we know that the core must be liquid. And then they'll start again in the inner core. So we have 4 planets, 4 terrestrial planets in our solar system. So everything I just told you is great for Earth, right? We have earthquakes, we have seismology, but what about on other planets where we don't have seismometers set up and we can't really tell what's going on in the interior? So one thing we have is meteorites from other planets. So I just really quickly want to show you how we know that we have meteorites from other planets. So let's take Mars, for example. We have a whole suite of meteorites from Mars. How do we know this? We know this because we know the composition of the gases that make up the atmosphere of Mars. And we also have meteorites where when they escaped the Martian atmosphere, they trapped little bubbles of the gases as they left the Martian atmosphere. And so by measuring the gases trapped in these meteorites, we know that they have the exact same composition as the Martian atmospheric gas that we've been able to measure through landers and orbiters around Mars. So we have meteorites from other planets, so that's very helpful. We can learn a little bit about what's going on there. We have rovers that around here you probably know pretty well. And we have orbiters. So this is the MESSENGER mission that orbited around Mercury. But what can we learn about planets from orbiters, for example? Well, it turns out that figure skating can teach us a little bit about planetary science. So when a figure skater spins, right, she's spinning, but she wants to start going a little faster. And so she brings in her hands and her legs, and as she brings them in, she spins faster and faster and faster. This is called a moment of inertia, and this is how we know what goes on inside of planets. Because the more mass you bring inside, closer to your axis, the faster you spin. So if a planet has more core than mantle, more dense core, it will spin faster than a planet that doesn't. And so by measuring the moment of inertia of planets, we can learn more about what it looks like on the inside. So instead of looking at the planets like this, I look at the planets like this, okay? So I look inside the planets. I want to know what's going on inside, what the layers look like, how big they are, and how they ended up this way. So each planetary body has its own unique pressure. So pressure is a function of size, temperature, and compositional space, what it's made out of. The 4 planets in our inner solar system don't have the same composition on the surface. They all look slightly different. And so as John mentioned, I conduct high pressure and high temperature experiments. And the reason I do that in order to understand about planets is that I can choose a pressure, temperature, and composition for each of my experiments and then see how that relates to the planets that I see. And so these are this is the equipment that I use in the lab. So I'll take you through this. This is called a piston cylinder apparatus, okay? So pressure equals force over area. The more pressure you put on something, the more force you put on something, the higher the pressure. So this piston cylinder and this multi-anvil put a lot of force on tiny little samples in order to get to very high pressure. So this is showing you what a capsule looks like that we put our samples in before we put it into this piston cylinder. It's a hydraulic press. It just uses oil pressure to control the force. This is a multi-anvil. For the multi-anvil, it can go to a bit higher pressure than the piston cylinder, so the samples get a little bit smaller. And this last one over here is called a diamond anvil cell. This one's the most interesting because instead of adding more force in order to increase the pressure, we just decrease the area. Okay, so we're kind of being tricky. We're trying to go the other way around. And the area is so small that it's just the top of the culet of the diamond. So we take two diamonds and we cut off the culet so that they're flat. And then we put a sample in between them, and then we put a little bit of force, and we get to very, very high pressure. And because diamonds are transparent, we can look right through them and look at our sample. So the pressures that we get at in the lab, so the pressure at Mount Everest, right, about 1 atmosphere, okay? The deepest ocean, about 1,000 atmospheres. The center of the Earth is about 3.6 million atmospheres. That diamond anvil cell can get beyond the pressure in the center of the Earth, and it can even make its way these days to trying to get at more giant planet-like pressures. Okay? The piston cylinder and the multi-anvil can't get as high, but the samples are much bigger, so they're easier to work with. I have to give a plug for the laboratory where I work because it's a really amazing place. And one of our most famous scientists was a man named Norman Bowen. And this is a picture of him in about 1950. And he's the one, he wrote a book called The Evolution of Igneous Rocks. He's the one who figured out that at different pressures and temperatures, different minerals will crystallize and you'll end up with different rocks. And then these men here are the first ones to ever reach in the laboratory a pressure of 1 million atmospheres. And this is Dave Mao. He still works at the lab with me. And so the Geophysical lab they were the pioneers for this diamond anvil cell research and for getting to very high pressures in the lab. So very quickly, this is a colleague of mine. His name is Yingwei Fei, and I wanted to give you a sense of what it actually looks like to do an experiment, because this is always something that's very hard to visualize. I showed you the equipment, but what is it actually, how does it actually work? And so what he's doing is he's taking a bunch of oxides. So we take normal rock compositions, and we mix them together in oxide form, and we add it to a bunch of metal. So metal and rock, right? We're trying to form a little planet. And we grind it together so that it's homogeneous for a really long time. And then we put it in an oven to get rid of all the ethanol and any water that might be in there. And then we put that oxide mix, that composition, into a tiny little capsule that we hold with tweezers. And then that goes into a zirconia octahedra, which then go into these 8 tungsten carbide cubes, okay? And the wires you see are thermocouple so that we know the temperature of the experiment. And we take that cube and we put it into the multi-anvil apparatus. We hook up the thermocouple so that we can make sure we know the temperature. And then we crank up the pressure and temperature. And we leave it up there at the conditions that we want for as long as we want. Okay, so you can see this experiment was done at 1800 Celsius, probably at about like 10 gigapascals, which is about 1,000 atmospheres or so. And then we cut the power off really fast to quench very quickly what's going on in that experiment. We want to know what was going on during the experiment, so we cut off the power very, very quickly so that everything freezes in place. And then we take it out, and we look at it, and we formed a little planet, right? So we have a mantle, we have a core, it's very cute. My kids really love it. And then sometimes we get, a bunch of little cores, and then we polish it, and then we analyze what we see within that experiment. So what we see in the lab is on the order of centimeters, right? But what we're trying to discuss and we're trying to simulate is something much, much bigger. Everything I just told you is stuff that is research that's been going on at the lab for decades, okay? So doing these experiments and measuring the chemical composition of the experiments has been going on for a very long time. But in my research, and something that I've brought to the lab, is that I add an extra layer to this research, and that is I study isotopes. So what is an isotope, okay? So if we look at the element iron, okay? Iron has an atomic number of 26. So what does that mean? It means it has 26 protons, okay? But really, there are 3 different forms of iron. All of them have 26 protons, but they have different numbers of neutrons. And this changes their mass slightly because neutrons have mass. So we have the same number of protons, different number of neutrons. It's all iron, but because of that tiny little difference in mass, it actually causes the different isotopes to behave slightly differently. And that slight difference, I will argue, will tell me a lot more about how a planet formed than just looking at the chemical composition. So I'm not just looking at the chemical composition of the mantle and the core. I'm actually measuring the isotopes in that mantle and in that core and looking at the comparison of the two. I do that with this instrument, which is called a mass spectrometer. And so what you do is you put your sample in one side of it. It goes through an electrostatic analyzer and a magnet. And here, it just collects the different masses. Okay, so you measure how much iron 54, how much iron 56, how much iron 57. And then you just look at why they're different from one another. Okay? So here we have our 4 terrestrial planets' interiors. I told you that they had iron in them, but actually there's more than just iron. Okay, there's iron, there's a little bit of nickel, and there's other stuff. So why do we think that there's other stuff? Well, if you look at the density of pure iron at the conditions that the core is at, there's actually a slight difference between iron and the core. And so there's something else in the core, and it's light because it's causing less density, okay? So what is that light element in the core, and is it different between the 4 terrestrial planets? So I'm going to take you through 2 or 3 very short examples of how we use isotopes to tell us what's in these cores, okay? So the first is we're just looking at silicon isotopes. So it's just like iron. It has 3 stable isotopes. And if you look at the silicon isotopes of the Earth versus meteorites, and these are those chondrites. Remember, chondrites are supposed to be the exact same starting composition as the Earth. So why would their isotopes on Earth versus those of chondrites be different? Nobody had any idea. So we did experiments in the lab, and we found that when you separate a core from a mantle, you suck out some of the isotopes into your core. And if you look at that, and you can plot it as a function of temperature. And so you know what temperature the Earth formed at approximately. You can say exactly what the silicon isotope ratio would be that would be different between the metal and the silicate. And when you do that, it lines up exactly with the meteorites and the Earth. And so by doing these experiments, we've been able to determine that there's silicon in the core of the Earth, along with the iron and the nickel. And we can say about how much as well. The same thing can be done for Mercury, except on Mercury, we don't have any meteorites for Mercury. Mercury's too close to the sun. Any meteorite that gets flung off of Mercury will not come back out to the Earth. It'll probably go into the sun instead. So we don't think we have any meteorites from Mercury. But we can do the same sort of thing. So this is the Messenger mission that orbited Mercury. And based on their data, they were able to determine that there's a solid iron core for Mercury, a molten core with iron, sulfur, and silicon, and then this FeS layer. Now you'll notice that Mercury is mostly core. Why is Mercury mostly core versus the Earth, which is core plus this huge mantle? Well, if you think back to those giant impacts that I showed you for the Earth, for example, it's thought that there was a giant impact that hit Mercury so hard that its mantle got stripped off of it and just flew into the sun. And so the only thing that's basically left is this giant core of a planet. But if we don't have meteorites for Mercury, or at least we don't think we do, every now and then a scientist will tell you that they found a meteorite for Mercury, but it's very hard to tell whether or not there really is one. And so we thought, okay, well, if this is true, and there's this much silicon in the core of Mercury, then we can tell you what a Mercurian meteorite would look like in isotope space. So now the next time someone says they think they have a meteorite from Mercury, we can tell them to measure the silicon isotopes in that meteorite, and then we can know whether or not it really is from Mercury. So there are people actually going through museums trying to do this. What about Mars? So Mars is super interesting because we've done a lot of research on Mars. We know a lot about Mars between the rovers that have been there and the orbiters. And a lot of work has focused on the interior of Mars. There's actually a NASA mission that was supposed to launch this year, but will probably launch in 2 years, called InSight, that's going to put a seismometer on Mars. So we're going to know a lot more about the interior of Mars. So Mars is thought to have a lot of sulfur in its core, okay? So we did experiments where we looked at the iron isotopes that would be in the mantle of Mars as a function of the amount of sulfur. And what we found is that while the Martian meteorites have the same iron isotopes as chondrites, according to our experiments, they should be way out here. And so this idea that Mars has a ton of sulfur in its core, we actually think is wrong. We actually think that there's much less based on these experiments. So what about pressure, right? So the Earth is really, really big, and it has a lot high pressure compared to Mercury, for example, or Mars. So what happens if we do our little isotope study, but we do it in the diamond anvil cell, if we bring it to really, really high pressure? Now, for many, many years, it's been thought that pressure has no effect on isotopes. So when I was in graduate school, I would hear this all the time from professors, that pressure has no effect on isotopes. It's been shown since the 1950s. And it kind of becomes dogma, right? Like people just say it over and over and over again. And so I'm a little stubborn, and so I decided that I wanted to see this for myself. Okay, so in the last couple of years, I've spent a lot of time trying to look for an isotope effect at high pressure. And what I just found a couple weeks ago is that pressure actually does have a very large effect on isotopes. And we can now use these isotopes to tell us not only about what's inside the Earth because it's at high pressure, but even more interestingly, one day, maybe not in my lifetime, but when we can measure spectra from exoplanets, right? If we could ever measure isotopes in those spectra, we'd be able to say what's in the interior of those exoplanets, because so many of the exoplanets are so big. So we started out with 4 terrestrial planets. We have interiors that look very different. Our focus for the future is to understand how what's going on in the interiors of these planets affects the surface, right? Because the interiors are going to be a certain composition based on the size of the planet and its history. What's inside is going to affect what's outside, right? So if you bring elements in to the core, for example, or to the mantle, they're not going to be on the surface anymore. And so the surface will then be different. Therefore, the atmosphere will also be different. And the atmosphere is today astronomically detectable. So how does the interior affect the surface, affect the atmosphere, affect life maybe? This is where we're trying to go in the future, right? This is complicated and requires a bunch of different types of scientists coming together and putting our heads together, trying to go from the inside out in order to understand more about these exoplanets that I showed you in the beginning of the talk. So the next time that somebody shows you an animation of Kepler, for example, right? So these, again, are the Kepler exoplanets that were found. But this time, more recently, somebody colored them relative to their temperature, not just their size. And so here's our solar system here, so you can see the difference. And what you see is this amazing diversity, all these different temperatures, all these sizes, all these different orbits. So the next time you see something like this, I hope that you not only think about what's going on the outside, but also how what's going on the inside can affect what's happening on the outside. And with that, I want to thank some interns I've had over the years and some postdocs whose research I just showed you, and of course the Carnegie Institution and NSF for funding. And I thank you for your time.
Here we have some questions.
Two questions, really. Am I right? Is there a seismometer on the moon? And could you comment on earthquake predictions on the moon and the Earth? And the second question is, early in the lecture you mentioned the disk solar system theory. Michael Brown says there's a ninth planet that's almost perpendicular to the disk of our solar system, and that kind of puts a glitch in your theory of the disk.
Okay, so
Can you repeat
yes, I have to repeat the question. So the first question had to do with moonquakes and whether or not there's a seismometer on the moon. As far as I remember, a seismometer was placed on the moon, but it was placed on the moon incorrectly. And so it's not actually touching the surface as well as it should. And so a lot of the measurements have been reanalyzed recently, and it's why we know that the moon has a core, is because a lot of the old data have recently been reanalyzed, and they have found that there's a moon on a core on the moon. So yes, and hopefully there will be one on Mars soon that will work very well. And the second question had to do with Planet 9, Planet X. So everything I told you about planet formation was figured out before we knew about all these other exoplanets and this Planet X that might or might not be in our solar system. And so you're right. A lot of it can change, and a lot of it will have to change, because a lot of those planetary systems that I showed you have planets that are in the wrong places. It doesn't make sense. How could something so big be next to a star and have smaller planets, further out? Like a lot of it doesn't really make a lot of sense. And so what I'm hoping you take away from this is that this is what we've thought until now, but over the last 6 years with Kepler, everything is going to need to be rethought. And so our hope in the lab is that the astronomers will inform us what they find, we will try to mimic it in the lab, and then we can kind of come up with a better and more encompassing theory.
Well, your theories are only applying to the rocky planets, but I assume a sort of same process would appear in the gaseous planets where kind of the denser gases would migrate to the core, could you theoretically apply some of the same principles to find out the composition?
Yes, so that's a great question. So he asked about the gassy giants, and he said a lot of what I said was about the interior terrestrial planets, and that's absolutely right. So there are two theories for how the gas giants formed. One is the same theory I showed you just now, core accretion, right? And the other is called disk instability. And one of our colleagues at DTM has done a lot of work on that. And so it's unclear exactly how they formed, but you're right, what we're trying to do, the reason we're trying to get to higher and higher pressure in the lab is because we're trying to understand more about the pressure inside the gas giants. It's thought that the gas giants also have a metallic core, but maybe a metallic core not made of iron. Hydrogen, for example, becomes metallic at a certain pressure. Okay, so it's very possible that the insides of these planets could have metallic cores, could have hydrogen cores, could have rocky portions. We're not sure, but the higher pressure we can get in the lab, the higher the pressure we can get in the lab, the closer we can get to understanding the interiors of the gas giants and the exoplanets that are so big.
Yeah, I'm assuming that the pressure at the center of the planet is zero, because everything's balanced around.
I'm sorry, this pressure at?
Pardon?
I didn't understand.
What's the pressure at the very center of the planet? Isn't it zero, essentially?
No, the pressure at the very center of the planet is 3.5 million atmospheres.
Well, if it's a sphere, doesn't everything cancel out as you get towards the center?
No, as you get inside, it gets more and more and more pressure. It's a function of depth. There's a lot of force. There's a lot of pressure in the center of the planet. That's why another reason we have an inner core is because the pressure is so high that the iron just turns solid again. It's no longer molten.
Yeah, you were talking about the effect of high pressure on the nature of the iron isotopes. What physically happens to the atom at 3.5 million?
That's a great question. So we hypothesize that as you're squeezing, things get more compact, right? And so the atom gets more and more and more compact. And what has to happen is that the bonds between the atoms need to get stiffer and stiffer and stiffer and stiffer. And so you're squeezing these things, and so their volume is going down. More importantly, the bonds are getting stiffer. And as the bonds get stiffer, the isotopes change.
So what happens to the electron orbits?
I assume that they get, if you think about the shape of the orbits and the atoms, they just squeeze. There's less space, I think, between the nucleus and where the electrons go.
Were you at all inspired by Rice Burroughs or Niels Bohr?
You know, I was inspired by Carl Sagan. I went to Cornell, and so for my undergraduate, and so I was very inspired by him and being in the same area where he used to teach. What would happen if you change the isotope ratio in the core? You mean what can we learn by that change, or would we notice a difference? There would be no physical difference that we would notice other than it would tell us about how it formed. So we would never notice. So nature gives a natural abundance of isotopes. There's just a natural abundance that exists. And how those change, we would never notice unless we measured them. But it can tell us about the process that caused them to change. Yeah.
You mentioned something about the accretion process that at about the size of a meter, what is it? Doesn't get much larger until you get to something
So there's a problem, there's a name for this problem that just escaped me, but there's a problem that when you have very small dust grains, they stick together through like electrostatic forces, right? They start to stick together. And then as you get bigger, things start to, they're not big enough to have a gravitational pull, right? So they just start to bounce off each other, and they don't really stick. And so there's this problem in the planet formation theory where you can get to a certain size, and you can, if you skip, a kilometer or so, then you can make it big again from gravitational pulls, or gravitational attraction. But in between, it's very hard, and people really haven't been able to figure out, as far as I know, how to get through that divide.
Have they looked at very fast collisions with smaller objects of that size and they just blow apart?
They blow apart. They don't really stick together as well. But a lot of those simulations, like the one I showed you for the giant impact, a lot of people do simulations and they do lab experiments also trying to piece it together. Yeah.
What about the technology of pressure? Because I gather you haven't reached a point where the pressures are so large that they cover the interiors of planets that you'd like to investigate. So often science follows technology.
Yeah.
And how's that?
So what we're trying to do is, it's actually very interesting. So technologically, what is the next thing that we can do in order to get to higher pressure, right? So we have these diamonds, and I told you that pressure equals force over area. So what we're doing now is we're making our own diamonds. So we have a CVD, chemical vapor deposition laboratory at the Geophysical lab, and we make our own diamonds, and what we're trying to do is we're creating the same shape, right? And then we drill a little hole within the diamond and put the sample in there. So the samples are getting even smaller, right? And it's even stronger because it's within the diamond. And so there are ways like that that we're trying to get at getting to higher pressure, changing the design of the diamond cell one way or another.
Do you think there's a limit?
I don't think there's a limit. I think technology, is amazing. Yeah. Yeah. So there's shear waves and compressional waves. Oh, I'm sorry. She wanted to know why certain waves don't go through liquid, whereas others do. So there's two types. There's shear waves and compressional waves. And the shear waves don't... so when you guys live in LA, so you have earthquakes, right? And there's different kinds of shaking, okay? And the compressional waves move in a certain way where they can go through anything because they move I don't know how best to describe it without a chalkboard. Yeah. So the shear waves basically can't move through liquid. They can't. There's no shear. I don't know. It just doesn't. The liquid doesn't shear, and so they can't go through the waves. I can draw it for you later. Yeah.
Is it really impossible to think about somehow getting something to the center of the Earth and getting over to the core and coming back? It's just totally impossible, or is that conceivable?
So I'm being recorded, so I need to be slightly careful. But the day before I left to come to LA, a colleague showed me a diamond. I told you that diamonds bring inclusions from the lower portion of the Earth. Oh, the question is, whether or not we could really ever get a piece of the core. And the inclusion in the diamond was metallic. It was a piece of metal, iron metal. And so the question is, where did that metal come from? Could this diamond have come from so deep in the Earth that it somehow grabbed a piece of the core, right? Or maybe not even a piece of the core, maybe a remnant of when the core formed or something, right? So that's one option, is these diamonds. The cool thing about these diamonds is that we get them from places like De Beers because they're really ugly, because they have tons of inclusions in them. So people don't want to buy them, right? So they give them to the scientists to do the research. And so we have tons and tons of diamonds that we can look at. So that's one option. And then there was a professor, maybe at Caltech, I'm not sure, who had an idea that he wanted to take a big chunk of iron and kind of put it into the earth and somehow watch it as it went through the earth. But that would take a really, really, really long time. So we can't physically ever get down there, but nothing's to say that we haven't figured out a way that maybe nature can bring it to us. We just need to find the right tracer. Are there any techniques of looking at the spaces between very small particles? Yes. So there's a synchrotron technique. So using synchrotron radiation, we can measure the volume and how the volume changes as a function of pressure. So that we can do. In terms of actually knowing the space, and I don't know, but I know for sure. Well, but X-ray diffraction is an option for knowing the crystal structure, and synchrotron radiation will tell you, can tell you the volume, but I'm not sure about inside of that volume how things change. Yeah.
My question is the measurement of isotopes actually tells you the development of the planet. Can it also give you an idea of the measurement of accretion over time, even though it happens in millions of years? But can it give you an idea of the rate of accretion?
Can isotopes help you learn about the rate of accretion? So there's two different types of isotopes. There's stable isotopes, like the one I just told you about, which have no time information. There's radiogenic isotopes, which decay at a certain rate. And so that's how we know how old the Earth is, right? That's how we know how old meteorites are, is by measuring the radioactive decay. And so there are ways people have used to, they use dating techniques for using these radiogenic isotopes in order to map out, when the solar system first formed, when the first solids in the solar system formed. So those are called calcium aluminum inclusions, and they're thought to be the first solids that formed in our solar system. So we know how old those are. And then we know how old the parent bodies of the chondrites are. And we know how old the Earth is. So using those sorts of dating techniques, you can kind of get a timeline for when we had tiny little specks to when we had more planetary sized, to when the moon formed. That sort of timeline can absolutely be obtained.
I'm still struck by what you said about potential compression of the electron shell of atoms.
Oh, that was hypothetical.
Well, I assume the change of the electron shell must somehow affect the nucleus, and is iron under extreme compression and temperature? Is it still iron? Does it look and act like iron, or does it have different properties in these extreme conditions?
It still acts like iron, but lots of elements do change their properties. So like I said, hydrogen becomes metallic, right? It's no longer a gas. There are lots of elements like that do change their properties, and you can watch it through a microscope as you're compressing. But iron, it goes through phase changes. So yes, okay, so all these elements will go through phase changes as you compress them, and so they'll no longer be stable if you do X-ray diffraction and you look at their crystal structure, it will shift, right, at a certain point, at a certain pressure, because they're no longer stable in that configuration. So they kind of twist a little bit to make a little bit, to fit in their new space. And so that does happen. And the properties of that phase change are different. So it has a different thermal conductivity. It does have different properties. That's correct. Oh boy. Does the core spin at a different rate than the rest of the Earth? I assume yes. It must, yes.
Considering stony iron meteorites, a combination, how is it possible that the inclusions could be there, stones, fragments, something I saw in the pictures there, in an iron matrix?
The question is, how could there be rock inclusions in an iron matrix? Yes. So are you talking about the pallasites, the ones that have the green chunks?
Yes.
So those are actually my current focus of my research because they're so fascinating. So one of the meteorites I showed you was this really beautiful one that was metallic and it had these green chunks. I didn't go into any detail about it because we're still trying to understand how they form that way. But the hypothesis over the last couple of decades is that those meteorites formed at the core mantle boundary of an asteroid, so where the core meets the rock. Now, that might be true. We don't really think that's true anymore. Some people now think that they were formed through impact. So a lot of what I told you tonight is newer research that the early solar system was very, very chaotic, right? That wasn't really what people thought a decade or two ago. And so a lot of impacts are now being used as the reason for what we see. And so one of the new hypotheses for pallasites is that a big asteroid hit another asteroid, melted the metal because the metal has a lower melting temperature than the rock. And then the metal kind of went around the rock, kind of filled in, little fragments, and then froze in place.
What's the pallasite made of?
It's iron, nickel, metal, and really beautiful green olivine crystals.
Okay, what's olivine?
Olivine is a magnesium silicate, and it's the main component of the Earth's mantle, and probably other mantles. Yeah, sure. Yeah. The density change, what is the density change when you compress samples? I don't want to make up a number. I think it's on the order of a few percent. I think so. Yes?
I have two questions.
Okay.
I teach third grade science.
Okay.
So when we talk about sound waves or light waves, so-called waves, in third grade, we use a slinky. And we could show compression waves
Oh, yeah.
and shear waves
Yes.
with a slinky.
That's the answer to your question. Yes. That's right. A slinky. That's a good, yes.
You get two kids on one end, on each end of the slinky.
Yes, and you do this, and you do this.
One kid gives, stretch it on the table, and then one kid gives a hard push, and you can watch that compression wave, and the kids can stop it, so you can see how they're all closer together.
That's brilliant.
Awesome. So that's the compression wave. The shear wave is obvious, because they just take it, they lay it on the ground, and they go wiggle, 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 and
Yes.
have this nice wave.
Did you hear that? Yeah.
Third grade science.
Yeah.
Okay?
Yeah.
Anyway, the other question I had was, in this formation, we now know that we have the Kuiper Belt and we have the Oort cloud. What's their development, and how do you include that in the...
So the question is about the Kuiper Belt and the Oort cloud, and I am not the expert on that. So I actually just met the person who discovered the Kuiper Belt at UCLA on Thursday. He's a professor at UCLA. So Pluto and all these dwarf planets, right, are part of the Kuiper Belt. And I'm not really sure. There's there are models for how the solar system formed that are newish, that involve the migration of planets, the giant planets, and the idea is that the giant planets kind of came in and disturbed what was going on and then kind of came out. And I don't know, maybe you know. No, I don't know much about how they formed, but I think it has to do with the migration of the giant planets.
With the molten core and tremendous pressure, are you still dealing with an incompressible fluid?
Are you still dealing with an incompressible fluid with a molten core at such high pressure? What do you mean?
Well, you're basically told usually like fluids are incompressible using different ways in engineering. But when you have those kind of pressures, is the fluid still incompressible?
I think so.
With the atoms being crushed down, is the fluid compressed?
I don't think so. I think it would still be, it would stay, whatever the compression is at that pressure, it would stay at, if that makes sense. Now, remember, the liquid core is convecting vigorously. That's why we have a magnetic field, right? And so I think it would still be an incompressible liquid. I have no idea. Is there a limit to the compressive strength of diamond? So we do break diamonds regularly. This idea that they don't break is not true. But they usually break when we make a mistake. So they usually break when the two flat sides are not perfectly flat, because then you're kind of like bending one right into the other, right? But when they're perfectly flat, to the eye of a human being, we can get them to pretty high pressure. But that is the biggest problem when we get to high enough pressure, is that the diamonds break. And that's been the reason why we haven't gotten to higher and higher pressure earlier, is that at a certain point, the diamond just breaks. And so a lot of people are trying to come up with materials that might be harder, but we can't. Not yet, at least.
I think we have, let's do one last question. Yeah, you got it.
Well, you had mentioned the magnetic field.
Yes.
By the core.
Yes.
Does that play a big part in research in other planets, studying magnetism and possibly how that affects the formation of the planet?
So for my research, what's interesting about a magnetic field is that, for example, Venus doesn't have a magnetic field, but Earth does. And Venus is very similar to the Earth in many ways, right? Mars had a magnetic field for a short amount of time, but no longer does. Mercury has a magnetic field. Magnetic field on Earth, we think, is there because we have the liquid and the outer core, right? So we have these conducting fluid with a big chunk of metal on the inside. So because of that, and because Venus doesn't have a magnetic field, we think maybe Venus doesn't have a solid core or doesn't have a liquid core, right? Mercury has both, and so it has a magnetic field. But there are astronomers who study magnetic fields on exoplanets, yeah, in order to understand more about magnetic fields. But for me, it's more interesting in my research for what it means about the core, because with or without the magnetic field, it's telling you something about the state of the core.
Can you create that geodynamo effect in the lab?
Can you create the geodynamo in the lab? So there's a professor at UCLA. I know a lot about UCLA because I went to school there. There's a professor at UCLA who has a huge tank of liquid metal that rotates, and they're trying to understand how magnetic fields are created. It's very cool. It's called the Spin Lab.
So I know we have more questions. You feel free to come up after Anat can answer some more questions.
Thank you.